The next great cyber conflict won't be waged with conventional code, but with qubits. We are entering an era where quantum machines are reshaping the foundations of both physics and digital security simultaneously. I'm your AI and quantum security architect, and today we're looking at the actual blueprint of the quantum advantage and why it's about to change everything. The core problem. Classical computers, using bits, process data sequentially or one at a time. When problems become too complex, like modeling 1 trillion chemical reactions, classical computers hit a wall called the classical limit, where finding an answer would take thousands of years. The quantum solution. Quantum computers use qubits, which can exist in multiple states simultaneously, or superposition. This allows them to analyze all possibilities at once, rather than one by one. The 3 pillars of value. 1. Time. Exponential speed. Quantum computing doesn't just make things faster, it collapses timescales. It can turn a calculation that would take a supercomputer 10,000 years into a task that takes 4 minutes. Energy. Efficiency. Since nature operates on quantum mechanics, atoms and molecules, classical computers have to use massive energy to brute force simulations. Quantum computers operate on the same laws as nature, allowing them to simulate complex molecules for medicine or batteries with far greater efficiency. Quantum advantage. This is the industry goal. It is the tipping point where a quantum computer solves a problem that is impossible for a classical computer to solve in a reasonable time frame. Achieving this unlocks breakthroughs in drug discovery, climate modeling, and materials science. To understand the future of cybersecurity, you must understand the qubit. The old way, classical computing, your smartphone and laptop run on bits. A bit is like a light switch. It is either on, 1, or off, 0. It cannot be both. To solve a complex problem, it has to flick that switch on and off billions of times in a specific order. The new way, quantum computing, quantum computers run on qubits. Thanks to a principle of physics called superposition, a qubit can be in a state of 1, 0, or both at the same time. Why this changes everything? This allows for parallel processing. Classical computer solves a problem sequentially. Step 1, then step 2, then step 3. Quantum computer solves all potential answers simultaneously. This massive leap in processing power is why quantum computers will eventually be able to break current encryption standards, and why we need quantum security today. To understand why quantum changes everything, we have to look at the scaling blueprint. In computer science, we call this Big O notation. It's simply a measure of effort versus data. The red line shoots up aggressively. This represents our current classical computers. It follows an O of n path. It's linear. That means if you double the data, you double the work. It looks sustainable at first, but for massive problems, that red line becomes a vertical wall. It effectively hits a limit. This is the quantum realm. Thanks to algorithms like Grover's search, we achieve O of square root of n efficiency. Notice how it stays low. As the data grows, the effort barely increases. The gap between the red and cyan lines pulses or highlights. The difference between that steep red climb and this smooth cyan curve isn't just math. That gap represents quantum advantage. Where classical computers choke on complexity, quantum computers thrive. Let's translate the math into a reality check. Imagine you have a database with 10,000 entries. On the left, you see the classical reality. To find a specific item, a classical computer might have to check every single entry. That is 10,000 steps of computation. It is a brute force grind. Now look at the right. This is the quantum reality. Because of the quadratic scaling we discussed, the square root of n, the quantum system doesn't need to climb the whole mountain. It solves that same 10,000 entry problem in just 100 steps. We didn't just make the computer faster, we fundamentally deleted 9,900 steps of work. That is the power of efficiency at scale.
Let's talk about a critical, often overlooked advantage: energy and sustainability. Efficiency isn't just about raw speed, it's about viability. As our demand for computation skyrockets, classical systems are hitting a wall, requiring an exponential increase in energy just to keep up. That is simply unsustainable. Quantum algorithms, however, grow sublinearly. This means we can tackle massive, complex problems without melting down our power grid. It's not just faster, it is a greener path forward for high-performance computing.
This advantage opens doors that have been locked for decades. We're talking about simulating complex proteins for drug design, modeling the chaotic physics of black holes, and securing the world's financial data with quantum cryptography. Essentially, the quantum advantage becomes a necessity whenever the variables of a problem exceed the capacity of traditional logic. Let's talk about the gold standard of modern digital security, SHA-256 encryption. To break this using brute force on the world's most powerful classical supercomputer would take a staggering 10 to the power of 58 years. To put that scale into perspective, our entire universe has only existed for about 14 billion years. When a problem takes longer to solve than the lifespan of the cosmos, we call that timeline effectively infinite. This is the infinite gap, and the quantum advantage is the only tool we possess that can collapse those impossible timelines down to something manageable.
So, why is this kind of speed even possible? It all comes down to the qubit. While a classical 0 and 1 flicker dully next to the vibrant sphere, while a classical bit is stuck as a simple switch, either a 0 or a 1, a qubit exists in a state of superposition. The sphere expands or glows brighter, numbers scrolling rapidly. This allows for exponential scaling. A system with just 100 qubits can represent more distinct states than there are atoms in the entire known universe. The sphere stabilizes, pulsing with energy. Think about that. We aren't just building a faster computer here. We are tapping into the fundamental fabric of reality itself. The unfinished bridge section emerging from the fog. Now, as an architect, I owe you a reality check. The blueprint is ready, but the materials are still being forged. The text NISQ era is highlighted or glows in the fog. We are currently standing in the NISQ era. That stands for Noisy Intermediate Scale Quantum. It means the potential is real, but the noise is high. We still need to improve qubit counts and coherence times by several orders of magnitude before the hardware fully catches up to the theory.
Now, the secret sauce of quantum computing isn't magic, it's physics. It is called interference. Think of it exactly like noise-canceling headphones. We use destructive interference to mute the probabilistic paths leading to the wrong answers, and simultaneously use constructive interference to amplify the path leading to the correct one. Ultimately, interference is the volume knob we adjust to find the truth hidden within the noise.
To summarize, we gain efficiency through superposition, sustainability through wave mechanics, and power through interference. The future of security is being written right now. If you found value in this blueprint, subscribe to AI Quantum Secure and join the conversation. I'm still learning, and I welcome you to explore this frontier with me. I'll see you in the next video. Ultimately, interference is the volume knob we adjust to find the truth hidden within the noise.